Welcome to Journey Through Time, a place where the boundaries of curiosity and calm blend together, inviting you to drift into vast cosmic stories while you unwind. Tonight, we set out on a journey that stretches far beyond the reach of ordinary experience. A journey not just across space, but back through the history of the universe itself. Here, under the soft glow of the stars and the quiet hum of the night, we will explore a story about beginnings, endings, and everything in between. It's a story about what happens when our most deeply rooted scientific ideas, the ones we've carried as certainties, are gently challenged by new light arriving from the depths of time. Imagine a silent golden eye, suspended a million miles from Earth, patiently gathering light that began its journey before our planet's oceans existed, before our sun was born, before anything we recognize had taken shape. This is the James Webb Space Telescope, a machine designed not only to look far into space, but also far into the past. Its giant honeycomb mirrors glint like an otherworldly sculpture, but their purpose is precise: to collect ancient photons, each one a tiny messenger from the dawn of creation. Instead of thrusting us into the future like a science fiction time machine, Webb brings the distant past forward, showing us the newborn universe as it once was. For over half a century, we've relied on the Big Bang model as the anchor for our cosmic timeline. This model says that roughly 13.8 billion years ago, everything we see today exploded out of an unimaginably hot, dense point and has been expanding ever since. It's a story that shaped not only physics textbooks, but also our cultural shorthand for the beginning of everything. And yet, as Webb's golden gaze pierces deeper into the darkness than any telescope before it, it finds galaxies that are too large, too bright, too mature to fit neatly into that early cosmic era. It's like opening a nursery and finding full-grown oak trees among the seedlings, a moment of astonishment that forces scientists to stop, reevaluate, and wonder what they may have missed. As you listen, take a breath. Think about where you are right now. Maybe it's night where you are, the world around you quiet, your mind settling into a slower rhythm. Or maybe it's the middle of a busy day, and you're sneaking a moment of stillness between tasks. Wherever you are, you're sharing this moment, traveling back billions of years through a voice and a screen, joining a story that began long before human life existed. This is the gentle paradox of science and wonder. In peering outward, we also peer inward, finding our own place in the vast and ancient unfolding of the cosmos. And so, as our story begins, allow yourself to drift. Let the old light of the universe wash over you, and together we'll begin to unravel how the James Webb Space Telescope, the quiet golden time machine, is transforming everything we thought we knew about the first galaxies, the birth of stars, and the earliest chapters of cosmic history. The James Webb Space Telescope does not simply look outward. It stretches our perception of time itself. Suspended at the second Lagrange point, a million miles from Earth, Webb sits in a perfect pocket of gravitational balance, its vast 5-layer sun shield blocking heat from the sun, Earth, and Moon, keeping the instruments colder than deep space so they can listen to the faintest whispers of light. This golden eye was built over decades, piece by piece, across countless labs and clean rooms. Each mirror segment of gold-coated beryllium was tested, folded, and unfolded like an intricate puzzle. The telescope's journey into orbit was itself a gamble. One misstep could have turned billions of dollars and thousands of human hopes into a drifting piece of space debris. But everything worked. The sun shield deployed, the mirrors aligned, and the instruments cooled. What Webb collects are not ordinary images. Each one is an archive of ancient light, stretched by cosmic expansion into the infrared. Because the universe is not static, but constantly expanding, wavelengths from the earliest stars are lengthened like rubber bands. A photon born in ultraviolet or blue light leaves its star as a young traveler, but arrives at Webb as a faint, reddened whisper, carrying the scars of billions of years of travel. This is why Webb's instruments are tuned to infrared, to catch signals that our eyes cannot see, to reveal galaxies that are otherwise invisible. Almost immediately after launch, Webb began returning images that astonished even seasoned astronomers. Instead of empty dark skies dotted with a handful of faint smudges, Webb's deep fields revealed a riot of galaxies, spirals, ellipses, irregular forms, some distorted by gravitational lensing into arcs and streaks. Each image is like opening a door into a vast hall, only to realize the hall is part of a palace, and that palace stretches beyond sight. But hidden within this grandeur is a disruption. The early universe, as predicted by models, should have been chaotic, dominated by dark matter and gas slowly gathering into shape. It should have taken hundreds of millions of years for stars to ignite in sufficient numbers to form galaxies. Webb found otherwise. The telescope's first deep field images showed galaxies far older and brighter than any cosmologist had expected to find at such distances. According to established timelines, galaxies in the first few 100 million years after the Big Bang should have been small, irregular, and poor in heavy elements. Yet Webb discovered massive structures enriched with carbon, oxygen, and other elements that could only have been forged in multiple generations of stars. This implies a cosmic speed-up, that star birth, death, and enrichment must have unfolded with astonishing rapidity. Consider the analogy of planting a seed. According to our understanding, it should take years for a tree to grow from a seedling to maturity. Yet Webb's data is showing us full-grown forests where only sprouts should be. Glass Z13 and Sears 93316, galaxies catalogued with technical names but unforgettable implications, appear to have formed as early as 235–300 million years after the Big Bang. In the compressed calendar of cosmic history, they appeared just days after creation. Yet they already contain billions of stars, implying a rate of assembly that defies conventional physics. One possibility is that the first stars, so-called population 3 stars, were far more massive than today's, burning fast and dying young, enriching their surroundings quickly. Another possibility is that dark matter played an even more dramatic role, clumping ordinary matter together with gravitational force far faster than predicted. Yet even these adjustments strain the limits of our models. To account for these galaxies, star formation must have been extraordinarily efficient, or the universe itself must have expanded differently than we assume. Each scenario forces astronomers to rethink the script of the early universe. Webb's images are more than just scientific puzzles. They are mirrors reflecting back our assumptions. For decades, the Big Bang theory was not simply one model among many, but the backbone of cosmology. It described an expanding universe that began as a hot, dense state and cooled over time. It explained the cosmic microwave background, the abundance of light elements, and the large-scale structure of galaxies. It seemed untouchable. Yet the galaxies revealed by Webb hint that our picture of how quickly structure emerged after the Big Bang may be incomplete. This is not the first time cosmology has faced upheaval. When Edwin Hubble discovered the redshift of galaxies in the 1920s, he overturned the notion of a static universe. When the cosmic microwave background was discovered in 1965, it validated the Big Bang, but forced scientists to refine their ideas about the early state of the cosmos. When dark energy was identified in the late 1990s, it upended the assumption of a slowing expansion. Each time, a shockwave of data forced a new equilibrium of theory. Webb's findings may be the next such shockwave. Astronomers have begun to whisper about impossible galaxies, structures that seem to have skipped cosmic childhood. These galaxies are not just bright. Some show disk-like features, hinting at organized rotation, a level of structural maturity thought to take billions of years to develop. Others appear to harbor supermassive black holes at their centers, which would require enormous seeds or exotic formation mechanisms to exist so soon after the Big Bang. Instead of being endpoints of slow evolution, black holes may have been participants from the start, shaping galaxies as they formed. The implications of these discoveries reach far beyond astronomy. They touch on how we understand time, growth, and the unfolding of complexity. In everyday life, time feels orderly. We wake, we eat, we work, and events follow one another predictably. Cosmology borrowed that sense of order. Big Bang first, then cooling, then stars, then galaxies. Webb shows us that the universe may have raced ahead, compressing eons of growth into cosmic instants. The very tempo of creation may have been faster, stranger, and more chaotic than we believed. Light itself is the key to this revelation. Every photon Webb detects left its source billions of years ago. The farther the source, the older the light. Observing distant galaxies is like leafing through an ancient photo album in which each page shows not a moment, but an epoch. Yet when we turn those pages with Webb, we find images out of sequence, mature galaxies appearing where only youthful smudges should be. This forces us to reconsider the physics of star formation, the behavior of dark matter, and even the underlying assumptions about cosmic expansion. None of this means abandoning the Big Bang entirely. The evidence for an expanding universe and a hot, dense early state remains overwhelming. But it does mean embracing uncertainty, acknowledging that our maps of the early cosmos are incomplete. Science thrives in these moments, when the data diverges from expectation and forces a deeper understanding. Webb's images, far from undermining cosmology, may herald a new era of discovery in which we refine our models and uncover hidden mechanisms of creation. In doing so, they remind us that even the most established theories are only provisional stories, waiting to be rewritten by the light of new evidence traveling across time. To understand why the James Webb Space Telescope is transforming our view of the early universe, it helps to slow down and consider the raw mechanics of light, distance, and time. Light, though unimaginably fast at 300,000 kilometers per second, is still finite. This means everything we see is delayed. Even the sun, which feels immediate to us, is in fact 8 minutes in the past. When you stand in sunlight, you are bathed in photons that left the solar surface while you were still in the middle of a thought or mid-sip of your drink. The moon is a second and a half away. Mars minutes. Proxima Centauri, 4 years. For nearby things, this lag is negligible. But for the farthest reaches of the cosmos, it stretches into billions of years. Webb's genius lies in embracing this lag rather than fighting it. It was built not to view the present, but to view the past, turning delay into a portal. Its infrared eyes are tuned to detect the stretched-out whispers of ancient photons, radiation that began its journey before Earth existed. Each photon carries with it a record of the conditions it left behind, its wavelength stretched by expansion, its path bent by gravity, its energy diminished by time. When these photons finally fall upon Webb's detectors, they become data points that can be combined into images, spectra, and maps of the early universe. Think about the sheer patience built into this arrangement. A photon launched from a newborn star 13 billion years ago travels through a cosmos that itself is changing, expanding, creating, and erasing structures. It crosses voids, brushes past dark matter halos, slides around black holes, threads between clusters. Civilizations rise and fall on tiny planets during its journey, and yet the photon knows nothing of this. It simply moves. Only at the end of its path does it find a mirror built by a species not yet imagined at its departure. That mirror reflects it, focuses it, and an instrument records its presence as an electric pulse. In that moment, the entire journey collapses into a single point of knowledge. Webb's images are therefore not snapshots in any familiar sense. They are time capsules. Every point of light in a deep field is a relic. Some of the galaxies in those images may no longer exist as we see them. They may have merged, dispersed, or been swallowed by black holes. We are witnessing their youth long after their maturity or death. This is why astronomers call telescopes like Webb time machines. They do not show the cosmos as it is. They show it as it was, layered like tree rings, each deeper view corresponding to an earlier era. This has profound consequences for cosmology. If the early universe really did produce mature galaxies far sooner than expected, it means our understanding of the timeline itself must change. Either the physics of star formation and galaxy assembly is much more efficient than our models allow, or the framework of cosmic expansion needs revision. Webb's data is not merely a set of pretty pictures. It is a challenge to decades of consensus, a whisper from the past telling us we have misread the opening chapters of the cosmic book. To appreciate how radical this challenge is, consider the history of the Big Bang model itself. In the early 20th century, the universe was widely thought to be eternal and unchanging. Einstein's equations of general relativity initially predicted either expansion or contraction, but he inserted the cosmological constant to preserve a static universe, later calling it his greatest blunder. Then Edwin Hubble measured the redshifts of galaxies and found they were receding, showing that the universe was expanding. This expansion implied a beginning, a hot, dense state in the past from which everything emerged. In 1965, the discovery of the cosmic microwave background sealed the case. The Big Bang moved from speculation to standard model, explaining not only expansion, but the abundance of light elements and the large-scale structure of the cosmos. By the late 20th century, the Big Bang was so successful that alternative models like steady-state cosmology faded into obscurity. Observations of the cosmic microwave background by Kobe, W. Mapp, and Planck confirmed its fine-grained predictions. Even the discovery of dark energy in the 1990s, which revealed that the expansion of the universe was accelerating, fit into the framework by adding a new ingredient. In this model, the early universe was hot, dense, and relatively simple. Matter gradually cooled, collapsed, and formed stars and galaxies. Large-scale structure emerged slowly, in stages, over billions of years. This is the model Webb inherited, the model its designers expected to confirm and extend. The telescope's unprecedented resolution and infrared sensitivity were meant to reveal the earliest faint smudges of galaxies, the baby pictures of cosmic infancy. Instead, Webb found not babies, but adolescents and adults scattered throughout the first few 100 million years. Glass Z13, Sears 93316, and other impossible galaxies do not just tweak the model. They strain its core assumptions about how quickly complexity can arise. Astronomers are therefore entertaining new possibilities. Perhaps the initial conditions of the universe were different than assumed, with density fluctuations or dark matter behavior that seeded structure more rapidly. Perhaps the first stars were extraordinarily massive, burning hot and short, and producing heavy elements at an accelerated rate. Perhaps supermassive black holes formed directly from collapsing gas clouds rather than through slow mergers, acting as gravitational anchors for early galaxies. Each of these ideas stretches existing physics, but does not necessarily break it. Yet together, they imply a cosmic childhood, more dynamic and less orderly than the Big Bang narrative suggested. This is the essence of scientific progress. Models are refined to accommodate new evidence. But the process can be jarring, especially when the evidence accumulates quickly. Webb's first year of observations produced more anomalies than some scientists expected in a decade. Peer-reviewed papers, conference talks, and preprint servers are now filled with debates about cosmic dawn. The field of cosmology, once relatively stable, is once again in flux. The deeper we peer into these questions, the more the line blurs between observation, theory, and philosophy. The James Webb Space Telescope has forced us to confront not only the mechanics of star formation, but also our assumptions about time itself. When we say 300 million years after the Big Bang, we picture a certain sequence of events, as if the universe were following a scripted play. But what if that script was more like jazz, improvisational, chaotic, leaping ahead in places and slowing down in others? What if our neat divisions of cosmic childhood, adolescence, and maturity are human projections onto something far more fluid? Light itself teaches us humility. Every photon Webb captures has survived an unimaginable journey. Some of those photons passed near black holes and were bent by their gravity, a process called gravitational lensing. This bending can magnify distant galaxies, making them appear brighter or larger than they are. Astronomers account for this, but the possibility always lingers that some of Webb's impossible galaxies are partly illusions created by cosmic optics. Yet even after accounting for lensing, many galaxies remain suspiciously massive and mature. The role of dark matter looms large in this puzzle. Dark matter is the invisible scaffolding of the cosmos. It does not emit or absorb light, but its gravity shapes galaxies and clusters. If dark matter clumped faster or behaved differently in the early universe than we assume, it could have accelerated the formation of galaxies, allowing them to assemble far sooner. Another possibility is that dark energy, the mysterious force driving cosmic acceleration, behaved differently in the past, altering the pace of expansion. These ideas are speculative, but increasingly considered as astronomers struggle to reconcile Webb's findings with existing models. There is also the enigma of black holes. Some of the brightest early galaxies may be powered not by stars alone, but by supermassive black holes feeding voraciously on gas and dust. How such giants formed so quickly remains an open question. The standard picture is that black holes grow from stellar remnants, merging and accreting matter over billions of years. To reach billions of solar masses in a few 100 million years would require either massive seeds or entirely new mechanisms. If black holes indeed existed at cosmic dawn, they may have been active participants in galaxy formation, shaping the very structures that now puzzle us. Beyond the technical debates lies a deeper message. The universe is not obliged to conform to our expectations. Our models, however elegant, are approximations. They capture patterns, but not the totality of reality. Webb's images remind us that every scientific framework is provisional. The Big Bang remains powerful and predictive, but it may not be the final word on cosmic origins. The galaxies Webb reveals are not mistakes. They are teachers, offering new clues about the forces and processes at work in the early universe. For the listener, there is a quiet wonder in this uncertainty. As you drift off or lean closer to the screen, you are part of an unfolding story. Each photon that strikes Webb's mirror and becomes a data point also becomes a line in a larger human narrative. The narrative of exploration, curiosity, and humility before the vastness of space and time. We are not only discovering galaxies, we are discovering the limits of our own imagination and then pushing beyond them. When we imagine the early universe, we often picture a smooth, dark void, slowly filling with pinpoints of light. In reality, it was far more turbulent. After the Big Bang, the cosmos was a searing plasma of particles, too hot and dense for atoms to form. Only after about 380,000 years did it cool enough for electrons and protons to combine into hydrogen, allowing light to travel freely. That faint radiation, the cosmic microwave background, still bathes the sky today, the oldest light we can see. It is the baby picture of the universe at less than 500,000 years old. But between that snapshot and the galaxies, Webb now observes, lies a mysterious chapter called the Cosmic Dark Ages. During this time, the universe contained no stars, only diffuse gas and dark matter. Gradually, tiny fluctuations in density, quantum ripples amplified by inflation, grew under gravity, pulling matter together into clumps. Eventually, the first stars ignited, ending the Dark Ages and initiating the era of Ryanization. Webb's mission was designed to probe this hidden dawn, to see the first light of galaxies flickering on after hundreds of millions of years of darkness. What Webb has revealed is that this dawn may have been startlingly quick. Instead of a slow flicker, it looks like a sudden blaze. Galaxies appear mature, enriched with heavy elements, and in some cases vast enough to rival today's largest systems. This contradicts the gradualist picture. It's as if someone flipped a switch, and the universe leapt from darkness into complexity. If this is true, it suggests either unknown physics or a radical efficiency in the processes of star and galaxy formation. This is why astronomers talk about cosmic archaeology. Each photon Webb collects is like a shard of pottery from a lost civilization. By assembling these shards, scientists reconstruct not just objects, but processes. How quickly gas cooled, how rapidly stars ignited, how black holes grew, how dark matter guided the dance. In the same way that an archaeologist reads layers of soil, cosmologists read layers of time, decoding the ancient signals embedded in light. Beyond the technical puzzles, Webb's findings have a psychological effect on the scientists themselves. For decades, cosmology offered a sense of stability, a master narrative that connected the dots from the Big Bang to the present. To be confronted with evidence that the timeline may be compressed or reordered is to feel the ground shift beneath one's intellectual feet. Astronomers who once taught students that galaxies took billions of years to mature must now entertain the possibility that some formed in hundreds of millions. It is a professional vertigo as much as a scientific one. Yet this vertigo carries excitement. The history of science is a history of being wrong in fruitful ways. When Galileo turned his telescope to the heavens, he saw moons orbiting Jupiter, shattering the geocentric model. When Herschel discovered infrared radiation, he expanded our sense of the electromagnetic spectrum. When Hubble measured redshifts, he upended the idea of a static universe. Each time, Nature's refusal to conform to expectations produced deeper understanding. Webb may be playing a similar role, revealing a universe that is stranger, but also richer than we imagined. This richness extends to the interplay of matter and energy at cosmic dawn. Heavy elements like carbon, oxygen, and iron are forged in stars and scattered by supernovae. The presence of these elements in early galaxies implies multiple cycles of birth and death, compressed into a blink of cosmic time. Black holes may have acted as engines accelerating this process, their immense gravity funneling gas and triggering starbursts. Dark matter may have provided the scaffolding for rapid assembly. The interplay of these ingredients could produce a universe that looks impossible under old assumptions, but inevitable under new ones. Webb's observations also show us something about ourselves. They remind us that every scientific model is a human creation, a map drawn to make sense of territory we can never fully traverse. The map is not the territory. The Big Bang is not the universe itself, but our best attempt to describe it. As the map is updated, our sense of reality shifts. We are not losing certainty. We are gaining fidelity, a more accurate representation of a cosmos that was always more complex than our first drafts suggested. The James Webb Space Telescope also reframes how we think about time and distance in everyday terms. We tend to imagine space as a vast container we move through, but cosmology reveals a subtler truth. Space itself stretches, carrying galaxies apart, like raisins in rising dough. This expansion means that the farther we look, the older the light and the more stretched its wavelength. It also means that the actual distance to a faraway galaxy, now, is much greater than the time its light took to reach us. When Webb sees a galaxy 13 billion light-years away, that galaxy may now be over 30 billion light-years distant due to expansion. This stretching turns Webb into both an observatory and a chronometer. Each measurement of redshift is a timestamp, each spectrum a fingerprint of ancient conditions. By comparing these fingerprints across different galaxies, astronomers build a timeline of cosmic evolution. But when the fingerprints don't match the expected ages, it signals something missing in the story. Perhaps the tempo of expansion changed. Perhaps new physics operated under the extreme conditions of early time. Perhaps our interpretation of redshift itself needs refinement. Each possibility is radical, yet grounded in the data Webb provides. There is also the mystery of organization. Maturity in galaxies does not just mean mass, it means structure. Disk-like shapes, rotational coherence, and central bulges take time to emerge. Yet Webb finds hints of such organization far too early. This suggests that either galaxies found a shortcut to stability, or our theories underestimate the speed at which gravitational interactions can sculpt order from chaos. If black holes were present, their influence could accelerate this process, but that raises new questions about how the black holes themselves formed. For listeners, the grandeur of these ideas can feel almost mythic, but unlike myths, these stories are drawn from actual photons collected by a golden mirror in space. Each data point is a real measurement, a signal that traveled across a changing universe to reach us. The result is a tapestry of information as delicate as it is vast. In studying it, we are not just learning about galaxies. We are learning about the deep logic of reality, how matter organizes itself, how time unfolds, how complexity arises from simplicity. To glimpse the early universe with Webb is to read a script written in light. The cosmic microwave background, discovered in 1965, is the opening line of that script, a uniform glow of radiation from when the universe was only 380,000 years old. But after that line, there is a gap, the so-called Dark Ages, when no stars yet shone. This gap was meant to last hundreds of millions of years before the first galaxies lit up the sky. Webb has torn a hole in that assumption. Instead of a long pause, we see evidence of a rapid crescendo, an explosion of structure where darkness should have been. To understand why this is shocking, think of human history. We expect hunter-gatherers, then small villages, then cities, then nations, a slow ladder of complexity. Webb has instead shown us cathedrals and metropolises, arising almost immediately after the dawn of time. This implies that the underlying processes, the physics of history on a cosmic scale, operated far faster than we imagined. It's as though gravity, star formation, and black hole seeding had access to shortcuts we never conceived. These shortcuts may involve dark matter, acting as invisible architecture. Dark matter does not glow, but it weighs far more than normal matter. Its gravity pulls gas into clumps, where stars can form. If dark matter clumped earlier or more aggressively than models predict, it would create deep wells into which ordinary matter would rush, sparking intense starbursts. At the same time, black holes could form directly from collapsing gas clouds rather than from smaller stellar remnants, creating engines powerful enough to shape galaxies from the outset. This would explain the luminous cores and organized structures Webb is seeing. Such ideas are bold, but they flow naturally from the data. We can test them by studying the chemical fingerprints of these galaxies, their spectra. Heavy elements such as oxygen, carbon, and nitrogen leave distinct lines in a galaxy's light. If Webb finds these elements in high abundance, it will confirm that multiple generations of stars lived and died in a very short time. If it finds very few, it may mean the galaxies are dominated by primordial stars or black hole activity. In this way, each spectrum is like a DNA test of the early universe, revealing ancestry, environment, and hidden processes. The implications ripple far beyond astrophysics. Webb's findings challenge our assumptions about time, causality, and the emergence of complexity. In everyday life, we expect growth to be incremental. A seed becomes a sapling, then a tree. A child grows into an adult. We imagine the universe obeys similar rhythms. But what Webb reveals is that, at cosmic dawn, the tempo may have been radically different. Stars, galaxies, and black holes may have coalesced in a rapid dance, achieving maturity in a fraction of the expected time. This shift in tempo forces us to reconsider how we narrate cosmic history. If the first billion years were far busier than we thought, then many of our assumptions about later epochs may also need revision. For example, how did reionization, the process by which the first stars and galaxies reionized the neutral hydrogen of the cosmos, proceed? Traditional models assume a gradual, patchy process, driven by small, faint galaxies. Webb's findings suggest larger, brighter galaxies existed earlier, which could have reionized the universe much faster and more uniformly than expected. There is also the question of black holes. Some of Webb's earliest targets show signatures consistent with active galactic nuclei, blazing disks of gas spiraling into massive black holes. If these giants existed only a few 100 million years after the Big Bang, then either black holes formed through an unknown mechanism, or they grew at breakneck speed. This has profound implications for everything from gravitational wave astronomy to the formation of large-scale structure. Black holes may not be the end products of galactic evolution, but co-architects of cosmic dawn. On a human level, Webb's discoveries invite a sense of humility. We like to believe our theories can predict the universe with precision, but the cosmos is not a laboratory experiment. It is a living archive of processes too vast and ancient to fully control or replicate. Each time we build a more powerful telescope, we find not just answers, but deeper mysteries. This cycle of surprise and revision is the lifeblood of science. It is how our maps of reality grow more detailed, more subtle, and more true to the territory they depict. At its heart, the James Webb Space Telescope is a collaboration between thousands of people across decades. Engineers, scientists, technicians, and mission planners poured their expertise into a single goal: to see farther back in time than ever before. The telescope's golden mirrors, sunshield, and instruments are feats of precision engineering, but they also embody something more abstract: humanity's collective desire to know. Every image Webb returns is a triumph, not only of technology, but of curiosity. The willingness to reach for light older than our species and to be changed by what we find. This willingness carries with it a lesson about uncertainty. When the telescope was conceived, its builders imagined it confirming the Big Bang model, showing us the predicted faint, clumpy galaxies. Instead, Webb has delivered a far stranger and more exhilarating universe. This is not failure. It is success of the deepest kind. Science progresses not by confirming what we already believe, but by revealing where we are wrong, pointing the way to richer truths. For those listening or watching, there is a poetic quality to this. The photons captured by Webb began their journey long before Earth formed, long before life emerged, long before consciousness could imagine them. They traveled across a cosmos in which entire stars and galaxies were born and died. And now, at last, they are intercepted by a mirror built by a small primate species on a pale blue dot. This act of interception collapses billions of years of travel into a single human moment, a moment you are sharing now, through a screen or a speaker, as the story unfolds. Webb thus becomes not just a telescope, but a bridge between epochs. It connects us to the dawn of time, allowing us to witness the universe's first experiments with structure and light. In doing so, it also reflects something about us, that we are capable of building instruments to look back farther than our own existence, that we crave to understand our origins, and that we find beauty even in the challenge of being proven wrong. This is the deeper gift of Webb's discoveries. They do not diminish the Big Bang model. They enrich it, transforming it from a fixed picture into a living, evolving story, still being written by the light of ancient stars. As Webb's mission unfolds, astronomers are beginning to recognize patterns in the surprises. The impossible galaxies are not isolated outliers, but part of a larger trend, suggesting that the first billion years of cosmic history were far richer and more dynamic than the previous model allowed. This does not necessarily overthrow the Big Bang itself. The evidence for an expanding universe emerging from a hot, dense state remains overwhelming. What it does undermine are our assumptions about how quickly complexity can arise and how the earliest structures evolved. Consider the rate of star formation. In our own Milky Way today, new stars form at a measured, relatively sedate pace. In the early universe, that rate may have been orders of magnitude higher. Clouds of pristine hydrogen collapsed into enormous stars, burned furiously, and exploded as supernovae, enriching their surroundings in just a few million years. Galaxies assembled and merged repeatedly, feeding black holes and igniting bursts of new star creation. This accelerated cycle could explain why Webb is seeing galaxies that look old at such a young cosmic age. Dark matter may also have played a far more aggressive role. In standard cosmology, dark matter acts as a gravitational scaffolding for visible matter. But if its distribution or properties were different in the early universe, more clumpy or more interactive, it could have created deep wells of gravity that drew gas together at astonishing speed. This would have shortened the timeline for galaxy formation, allowing massive systems to appear far sooner. And then, there are the black holes. The traditional picture has black holes as end products of stellar evolution, growing slowly through mergers. Webb hints they may instead be seeds planted at the very dawn of time, either through direct collapse of gas clouds or through exotic mechanisms not yet imagined. These early black holes could have acted as engines for galaxy formation, their gravity funneling material and their energy triggering starbursts. If true, then our current concept of cosmic dawn must be revised to include black holes as co-creators of the first galaxies, rather than as latecomers. This revolution in understanding carries profound implications for our sense of time and ourselves. We tend to think of time as a single arrow, moving from simplicity to complexity in predictable steps. The early universe challenges that view. Complexity may arise rapidly under the right conditions. This is not just an astrophysical curiosity, but a philosophical insight. Under certain circumstances, the universe can assemble vast organized structures in a fraction of the time we expect. It also hints at the provisional nature of knowledge. For decades, the Big Bang model was the framework within which all other cosmological ideas fit. Webb's images have loosened that framework, revealing new degrees of freedom. This does not weaken science. It strengthens it by forcing deeper inquiry. The fact that a telescope can challenge a half-century of assumptions is proof of how alive and self-correcting the scientific process remains. For listeners or viewers, there is a kind of intimacy in this. We are not just passive observers of the cosmos, but participants in a grand conversation. Our instruments catch the whispers of ancient light, translate them into data, and then into stories. These stories shape how we see ourselves, not at the center of the universe, but woven into its unfolding. The light Webb captures is not only evidence of cosmic history, but a mirror for human curiosity, patience, and the urge to know. Looking ahead, the data from Webb will feed into new models and simulations. Cosmologists are already adjusting parameters for star formation efficiency, dark matter behavior, and black hole growth. Computer simulations that once took days now run for months, testing extreme conditions. The goal is to produce virtual universes that resemble Webb's observations, to see under what assumptions the impossible becomes inevitable. This iterative process, observation, model, revision, is how science converges on deeper truth. As the picture sharpens, it becomes clear that Webb is doing more than collecting data. It is redrawing the map of cosmic history. Each galaxy it reveals at high redshift is a landmark, a signpost from the past. Together they outline a landscape of rapid growth, unexpected structure, and perhaps new physics. This landscape will take years to survey, and even longer to understand fully. The telescope also changes how we imagine our place in the universe. To see light that began its journey before Earth formed is to experience a kind of temporal vertigo. Our entire species fits into a single pixel of the cosmic timeline, yet we have built a machine capable of looking back to the dawn of everything. This paradox of our smallness and our reach is at the heart of the Webb story. It also changes how we think about the future. If the early universe was more dynamic than we imagined, what does that imply about the later universe? About the eventual fate of cosmic structures? Perhaps the same forces that allowed rapid assembly at the start will shape the end in ways we cannot yet foresee. Webb's data will inform not only models of the past, but predictions of the future, from the behavior of dark energy to the ultimate destiny of galaxies. Finally, Webb reminds us that every act of observation is also an act of imagination. The photons it captures carry no inherent meaning. We supply that by building theories, running simulations, and telling stories. In this way, science and storytelling converge. Each spectrum is a sentence, each image a paragraph, each discovery a chapter in a narrative that stretches across billions of years. As you listen to this story unfold, you are part of that narrative, a mind in the 21st century, contemplating light that left its source in the first heartbeat of the cosmos. To explore the implications of Webb's discoveries, we must first return to the concept of light as an archive. Every photon captured by Webb is a messenger from an age so ancient that our familiar scales of time become meaningless. We compress billions of years into phrases like cosmic dawn or the first billion years, but these words fail to convey the immensity of what they describe. When Webb's detectors register a single faint photon from a galaxy at redshift 13, that photon left its source before the Milky Way existed. It passed through a universe of shifting gravitational potentials, expanding voids, and dark matter webs, a journey longer than all of human history, by orders of magnitude. This makes Webb not only a telescope, but an archaeological dig across time. Each deep field is a trench cut into the fabric of the past. The galaxies it reveals are like artifacts embedded in cosmic strata, telling stories of processes that operated before our planet's crust solidified. And like any dig, the deeper we go, the stranger the artifacts become. Instead of tiny fragments, Webb is uncovering monumental structures, galaxies with billions of stars, supermassive black holes feeding furiously, and chemical enrichment so advanced that it defies gradualist explanations. For astronomers, this means building new frameworks. Perhaps the laws of physics themselves behaved differently under the extreme densities and temperatures of the early universe. Or perhaps our understanding of those laws is incomplete, missing crucial variables that accelerate structure formation. Even the notion of time may need rethinking. Cosmic time is not absolute but tied to the expansion of space. If expansion proceeded differently in the early epochs, our sense of 300 million years after the Big Bang may be more elastic than we think. This elasticity could compress the perceived timeline, making galaxies appear impossibly mature when in fact the yardstick itself is shifting. But beyond these theoretical shifts lies a deeper, almost existential reflection. We are seeing the first sparks of order emerging from a primordial chaos. We are watching matter learn to form stars, stars learn to form galaxies, galaxies learn to form structure, a cascading hierarchy of complexity. And through Webb, we become participants in that learning, building models of processes that predate not only our species, but our planet. This reflection invites us to think about our own position in the cosmic story. We are used to imagining ourselves at the end of a long chain of events, the culmination of billions of years of evolution on a small blue world. Yet when we peer back with Webb, we see that even the universe itself may have a kind of adolescence, a period when it raced ahead, building vast structures with startling speed. This invites a humbling symmetry. Just as a child's early years shape the adult it becomes, the universe's first billion years shaped everything that followed, from the distribution of galaxies, to the formation of heavy elements, to the emergence of planets, and eventually, life. Webb thus offers more than data. It offers context. It shows us that our cosmic environment, the Milky Way, the Sun, the Earth, is the product of processes that began in that first billion years. The carbon in our cells, the oxygen we breathe, the iron in our blood all trace back to stars that lived and died long before the sun ignited. Seeing galaxies already enriched with heavy elements at cosmic dawn is to see the ancestors of our own atoms at work. This is not just astronomy. It is genealogy on a universal scale. It also reframes the Big Bang model as a living, evolving theory rather than a fixed doctrine. For decades, cosmologists spoke of it with the confidence of a map, long tested by explorers. Webb has revealed uncharted territories, showing that the map may need redrawing. This does not mean the Big Bang is wrong. It means the universe is richer. The model will adapt, as it always has, to incorporate new data, new physics, new insights. This adaptation is science at its most honest and most powerful. Finally, there is the emotional dimension. Webb's images evoke awe, not just because of their beauty, but because of their implications. They tell us we live in a universe that was busy, dynamic, and creative almost from the start. They show us that our deepest assumptions are provisional, and that discovery is an ongoing process. They remind us that humility and curiosity are not opposites but partners. As we move toward the conclusion of this cosmic journey, it is worth pausing to see what Webb has truly accomplished. It has not merely extended the reach of astronomy by a few billion years. It has altered our sense of time, maturity, and possibility. The telescope's golden mirrors have acted like a bridge across epochs, bringing us face to face with galaxies that by all rights shouldn't exist, yet do. This confrontation with the unexpected is the essence of science. Not a setback, but a sign that our understanding is poised to deepen. In practical terms, Webb's data will feed a generation of research. Cosmologists are already running new simulations, testing scenarios in which dark matter clumps faster, black holes form directly, or star formation proceeds at extraordinary rates. Observers are planning follow-up spectroscopy to pin down the chemical composition, ages, and distances of these galaxies with unprecedented precision. Theorists are exploring modifications to cosmic expansion, inflation, and the role of exotic physics. Each avenue represents a possible path to reconciling theory with observation. But beyond the research papers and conference debates lies the larger story, the one you are hearing now. This is a story about light traveling billions of years to meet an instrument built by beings who themselves evolved on a small world around an average star. It is a story about humility in the face of immensity and about the courage to revise our ideas when confronted with evidence. It is also a story about connection. The way photons from the universe's first galaxies now mingle with the neurons in your brain as you imagine them. In this way, Webb is not only a telescope, but a mirror of our own curiosity. It shows us the universe, but also shows us ourselves, our capacity to question, to build, to wonder, and to accept uncertainty. It reminds us that science is not a collection of fixed facts, but a process of continuous revision, a conversation between the cosmos and our minds. And as we prepare to enter the closing chapter of this narrative, we carry forward the realization that even our most trusted theories are provisional, and that the universe will always have more surprises in store. In reaching this point of the story, we've come to understand that the James Webb Space Telescope is not just a new instrument, but a new way of seeing. It forces us to abandon the comfort of familiar scales and accept that, at the universe's dawn, processes we thought would take eons happened almost overnight. This acceleration is not an inconvenience. It is a revelation. It tells us that under the extreme conditions of the early cosmos, Nature could organize itself with startling speed, producing galaxies, black holes, and heavy elements before our models would have thought possible. This invites a broader reflection on complexity itself. Complexity does not necessarily arise linearly. It can emerge abruptly when conditions cross a threshold, a principle seen in everything from phase transitions in physics to tipping points in ecosystems. In the early universe, thresholds of density, temperature, and gravity may have triggered cascades of star formation and structure assembly. Webb's observations suggest that such cascades were not rare anomalies, but the dominant mode of cosmic dawn. There is also a lesson here about observation and bias. Before Webb, the deepest surveys came from Hubble, which could see far but not far enough into the infrared to capture the faintest ancient light. Our picture of cosmic dawn was thus built on partial data, and our theories grew around those constraints. Webb lifted that veil and found a landscape more crowded and luminous than expected. This is not the universe changing. It is our view expanding. Each new instrument adds a layer of reality, reminding us that our models are only as good as our measurements. Finally, consider the symbolism. At a time when our species faces its own crises, we have built a machine to look back to the universe's first moments. This act of looking outward in the midst of our own challenges is itself a statement of values. It says that curiosity, exploration, and humility before the unknown are not luxuries, but essentials of being human. The next step for Webb and for cosmology is to map these early galaxies in greater detail. Already, follow-up observations are revealing their shapes, masses, and star formation rates. Spectroscopy, splitting the light into its component wavelengths, will allow astronomers to measure their chemical composition, internal motions, and even potential black hole activity. These measurements will test the competing scenarios for rapid galaxy formation. Extremely massive early stars, accelerated dark matter clumping, or direct collapse black holes. The outcome of these tests will not only refine our timeline of cosmic dawn, but also illuminate how the conditions of the early universe shaped everything that followed. The distribution of galaxies today, the cosmic web of filaments, clusters, and voids, is rooted in the initial density fluctuations amplified by gravity. By understanding how quickly and efficiently matter assembled at the start, we gain insight into why the large-scale structure looks the way it does now. This knowledge feeds into models of dark energy, the ultimate fate of the universe, and even the likelihood of habitable worlds. There is also a cultural dimension to these discoveries. Webb's images have entered popular consciousness, not just as scientific data, but as icons of wonder. The golden mirrors, the deep fields, the glittering arcs of gravitationally lensed galaxies. These have become symbols of humanity's reach. They remind us that science is not only about equations, but about awe, about the capacity to be surprised. In a world often dominated by short attention spans, Webb's images invite us to slow down, to contemplate timescales beyond imagination. In this sense, the telescope is a bridge not only between epochs, but between disciplines, between science and art, between data and meaning, between what we know and what we feel. As you listen to this story unfold, you are participating in that bridge, letting ancient photons enter your mind and spark new connections. All of this leads us to a larger truth. The universe is not a finished painting, but an evolving symphony. Each new observation adds an instrument, a motif, a counterpoint. The James Webb Space Telescope has not closed the book on cosmic history. It has opened a new volume. Its data hint that the early universe was a place of furious creativity, where stars, galaxies, and black holes emerged with astonishing rapidity. This creativity did not end with cosmic dawn. It continues today in the merging of galaxies, the birth of stars, and perhaps even in the emergence of consciousness, capable of reflecting on it all. This view reshapes our understanding of ourselves. We are not latecomers to a static cosmos, but participants in an ongoing unfolding. The atoms in our bodies were forged in stars that lived and died before the sun. The structures of our minds may reflect patterns established in the first billion years. To study cosmic dawn is thus to study our own origins at the deepest level. Looking ahead, Webb's legacy will be measured not only in scientific papers, but in imagination sparked. Children who see its images today may become the scientists who interpret its data tomorrow. Artists may translate its visions into new forms. Philosophers may draw from its discoveries to explore questions of time, causality, and emergence. In this way, Webb is not just a telescope, but a seed for future thought, scattering possibilities across generations. And so we approach the point where this narrative will circle back to its beginning, where the channel's name will once again appear as a signpost, framing the journey. In the final block, the story will close not with an ending, but with an invitation to keep exploring, to keep questioning, to keep following the light across time. As we push beyond the first chapters of cosmic history, Webb's data begin to map not just isolated galaxies, but the entire tapestry of large-scale structure. Filaments of matter stretch like invisible threads, connecting galaxy clusters across hundreds of millions of light-years. These filaments form a cosmic web, the skeleton of the universe shaped by dark matter's gravity. By looking back to when these structures were only beginning to form, Webb lets us watch the scaffolding of the cosmos assemble in real time. In this web, galaxies are not random islands, but nodes of a vast network. Gas flows along filaments, feeding galaxies and fueling new star formation. Gravity draws smaller systems into larger ones, mergers trigger starbursts, and black holes anchor the centers. All of this was once assumed to take billions of years. Now Webb hints it may have happened in a cosmic rush. The implication is that the cosmic web itself, the largest pattern in the universe, was imprinted and operational far earlier than we believed. This network also offers clues about dark matter's properties. If the filaments are denser or more coherent at early times, it suggests dark matter clumped strongly, accelerating structure formation. If they are more diffuse, it may imply new physics or interactions. By mapping how galaxies trace these filaments at high redshift, Webb acts as a cartographer of the invisible, translating ancient light into a three-dimensional map of the universe's hidden backbone. For us on Earth, this cartography is more than academic. It shows that the place we inhabit, a spiral galaxy on the edge of a filament in a supercluster, is part of a vast dynamic network, one that extends from cosmic dawn to the present. To look at the cosmic web is to see our own address in the universe, not as an isolated dot, but as part of an interwoven whole. The telescope also reaches beyond galaxies to study the first stars themselves. Known as population 3 stars, these hypothetical behemoths would have been almost entirely composed of hydrogen and helium, lacking the heavier elements forged by previous generations. They are thought to have been hundreds of times more massive than our Sun, burning hot and dying young in titanic supernova. Detecting these stars directly has been a holy grail of astronomy for decades. Webb's unprecedented sensitivity may finally make it possible. By capturing the faint signatures of their light or the chemical fingerprints of their explosions, astronomers can confirm their existence and properties. If population 3 stars did indeed form as theorized, they could explain the rapid enrichment of early galaxies. If not, then some other, more exotic process must have jump-started cosmic chemistry. This search is not just about the past, but about the foundations of everything familiar. The heavy elements in our bodies, carbon, nitrogen, oxygen, iron, were all synthesized in stars. To witness the first generation of stars is to watch the universe learning to create the building blocks of life. It is to see, for the first time, the factories where future planets and future beings became possible. Webb's data also provide clues to the Rayonization era, the period when ultraviolet light from the first stars and galaxies stripped electrons from neutral hydrogen, making the universe transparent to light. Measuring how and when this process occurred is essential to understanding how the cosmic dark ages ended. Webb's high-resolution spectra of distant galaxies allow astronomers to chart Rayonization as a function of time and space, revealing whether it was uniform or patchy, sudden or gradual. Another frontier Webb opens is the study of early black holes. Supermassive black holes, billions of times the sun's mass-power quasars, luminous beacons visible across the universe. Finding such objects at high redshift implies that black holes grew far more quickly than standard models allow. Webb's near-infrared spectrographs can detect the characteristic signatures of accretion disks, winds, and emission lines from gas spiraling into these monsters. By measuring these features, astronomers can estimate black hole masses, accretion rates, and even the geometry of the surrounding regions. The presence of these giants so early challenges not only our understanding of black holes, but also of galaxy formation itself. Perhaps galaxies and black holes co-evolved, each shaping the other in a feedback loop. Jets and winds from black holes can compress gas, triggering star formation, or expel it, quenching growth. This complex interplay may have operated at cosmic dawn with an intensity we can scarcely imagine. Webb also opens a window onto gravitational lensing, the bending of light by massive objects. Some of the most distant galaxies are visible only because intervening clusters magnify them, acting as natural telescopes. By studying multiple lensed images of the same source, astronomers can reconstruct the source's true shape and brightness, as well as map the dark matter in the lensing cluster. In this way, the universe itself provides magnifying glasses, and Webb is the eye behind them. These studies, combined, promise to transform our understanding of the earliest structures. They will reveal not just when galaxies formed, but how, under what conditions, and with what interplay of forces. They will clarify the role of dark matter, dark energy, black holes, and the physics of star formation in shaping the universe we now inhabit. One of the most striking aspects of Webb's early results is the way they force us to think of galaxies not as isolated islands, but as participants in an intricate cosmic ecology. Gas flows into galaxies along filaments. Stars form from that gas, supernovae, and black holes return enriched material to intergalactic space, and the cycle begins anew. This cosmic feedback loop may have been especially intense at the dawn of time, when densities were higher and gravitational wells deeper. Webb's ability to detect faint emission lines from distant galaxies allows astronomers to reconstruct this cycle in unprecedented detail. By measuring the relative abundances of elements, the temperatures of interstellar gas, and the presence of outflows, they can determine how effectively galaxies converted gas into stars and how rapidly they recycled material back into space. These measurements reveal that some early galaxies were veritable star factories, converting vast reservoirs of hydrogen into stars in bursts that lasted only tens of millions of years. a cosmic blink. The impact of such bursts is profound. They generate intense radiation fields, drive massive winds, and may even help regulate the growth of black holes. In effect, early galaxies may have been self-organizing systems, finding a balance between collapse and feedback much faster than expected. This accelerated feedback cycle could be the missing ingredient, explaining why Webb sees such mature systems at high redshift. It also reframes our picture of galactic evolution at later times. If galaxies began with such intense activity, then their subsequent settling down into more stable structures, like the Milky Way, may have been a long process of cooling, merging, and rebalancing. This would mean our own galaxy is the descendant not of quiet protosystems, but of ancient star-bursting titans. Another realm where Webb is breaking ground is the intergalactic medium, the diffuse gas that fills the space between galaxies. Though tenuous, this gas contains more baryonic matter than the galaxies themselves. It acts as the reservoir from which galaxies draw their fuel, and as the sink into which they expel their wastes. Understanding how the intergalactic medium evolved during cosmic dawn is crucial to piecing together the larger story. Webb's deep infrared spectra can detect the faint glow of hydrogen and helium in this medium, as well as absorption lines imprinted on the light from background sources. These signatures reveal how reionization progressed, how quickly the first ultraviolet photons escaped their host galaxies, and how transparent the universe became over time. By comparing regions of different density and distance, astronomers can map the patchwork of reionization, turning a theoretical process into a measured one. This mapping will also constrain the nature of dark matter and dark energy. The distribution of gas and galaxies traces the underlying gravitational potential. If dark matter is warm rather than cold, or if it interacts in subtle ways, it will alter the small-scale structure of the cosmic web. Likewise, if dark energy evolved over time, it will leave fingerprints in the way structures grew. Webb's observations thus feed directly into the deepest questions about the composition and fate of the universe. On a human level, there is something poetic about using a golden mirror to detect the faintest whispers of gas between galaxies billions of years ago. It is like listening to the breath of creation, the faint susurration of a universe becoming transparent to its own light. The telescope also gives us a chance to explore the physics of extreme environments, conditions we cannot reproduce on Earth. The cores of early galaxies, the surroundings of supermassive black holes, and the dense star-forming clumps at cosmic dawn all operate at pressures, temperatures, and densities far beyond our laboratories. By studying their light, we effectively conduct experiments across time and space, testing the laws of physics under conditions otherwise inaccessible. Already, Webb has detected signatures of complex molecules in some early galaxies, hints of dust, polycyclic aromatic hydrocarbons, and other compounds previously thought to emerge only later. This suggests that the chemistry of the cosmos matured quickly, creating the raw ingredients for planets, and ultimately for life. If dust and molecules were abundant so early, then the pathways to habitability may have begun much sooner than imagined. This has implications for the search for life beyond Earth. If the universe produced heavy elements, dust, and complex molecules in its first billion years, then rocky planets and prebiotic chemistry could have been widespread long before our sun formed. This does not prove life existed then, but it expands the window of possibility. Webb's ability to detect exoplanet atmospheres, even in distant systems, adds another dimension, connecting cosmic dawn to the prospects for life across the galaxy. At the same time, Webb's precision tests our deepest physical theories. Any deviation from expected spectral lines, any unusual ratio of elements, any unexpected pattern of galaxy clustering could signal new physics, from exotic particles to modifications of gravity. In this way, the telescope is both a window and a crucible, revealing and testing simultaneously. As Webb continues its mission, it has begun to link the earliest moments of cosmic history with phenomena we observe in the nearby universe. Galaxies at high redshift are no longer abstract points on a graph. They are ancestors of the structures we inhabit today. By studying their properties, astronomers can trace the lineage of our own Milky Way and its neighbors, seeing how patterns of mass, rotation, and star formation were imprinted billions of years ago. One of the most intriguing aspects of this lineage is the role of mergers. In the present-day universe, galaxies grow by colliding and combining, their shapes distorted and their star formation triggered by gravitational interaction. Webb's images show that this process began very early, with small systems merging into larger ones under the influence of dark matter halos. Some of the bright, massive galaxies at cosmic dawn may in fact be clusters of smaller galaxies, merging so rapidly they appear as a single entity. This perspective transforms our view of cosmic history from a static family tree into a dynamic process of continual reshuffling. The Milky Way, Andromeda, and every galaxy we see today are products of countless mergers and accretions stretching back to cosmic dawn. Understanding these processes at their inception helps explain not only galactic structure, but also the distribution of stars, the location of black holes, and the abundance of heavy elements. This insight extends to the chemical evolution of the universe. Each merger mixes different stellar populations, redistributing metals and dust. Webb's spectroscopy can detect subtle differences in elemental abundance between merging components, revealing how chemical gradients evolved over time. This is like reading a cosmic recipe book, tracing the ingredients of our own planet back to the first kitchens of the cosmos. Another major arena where Webb is reshaping knowledge is the interplay between light and matter in the early universe. The rionization process, once thought to be gradual and patchy, now appears to have been driven by surprisingly bright, massive galaxies capable of flooding the intergalactic medium with ionizing radiation. This changes our estimates of how quickly the universe became transparent and how soon large-scale structures emerged. By capturing faint Lyman alpha emission and absorption lines, Webb maps the boundaries of ionized regions around early galaxies, cosmic bubbles of transparency expanding into the neutral hydrogen fog. The size and shape of these bubbles reveal how quickly the ultraviolet radiation escaped, how clumped the gas was, and whether feedback from black holes or supernovae accelerated the clearing. This mapping also intersects with gravitational lensing, as light from background galaxies passes through these regions, gaining or losing energy, depending on the intervening matter. Combining these observations yields a three-dimensional portrait of cosmic dawn, where matter, light, and gravity weave a tapestry of structure and change. For human observers, the effect is to collapse incomprehensible distances and times into a single image or graph. Webb's data transform billions of years into visible patterns on a screen. In that act, it also transforms our mental model of the universe, from a linear narrative to a network of simultaneous processes unfolding across scales. Webb's reach does not stop at galaxies. Its sensitive instruments are also probing the formation of stars and planetary systems in the nearby universe, providing a bridge between cosmic dawn and our own origins. By observing star-forming regions in our galaxy with unprecedented clarity, Webb reveals how gas collapses into protostars, how disks form around them, and how dust grains stick together to become planets. This local insight feeds back into our interpretation of the early universe. The same physics that shapes stars today operated then, only at vastly different scales and tempos. The telescope's ability to detect complex organic molecules in star-forming regions hints at the universality of chemical pathways. If such molecules are common in our galaxy, they may also have formed in the first dense clouds after the Big Bang. This means the seeds of biology could have been scattered widely across space and time, making life a cosmic rather than a purely planetary phenomenon. At the same time, Webb's data on exoplanet atmospheres is extending the search for habitability beyond our solar system. By measuring how starlight filters through an exoplanet's atmosphere during transits, Webb can detect gases like water vapor, methane, or carbon dioxide. This capability, combined with its view of cosmic dawn, creates a unified picture. From the first galaxies to potentially life-bearing worlds billions of years later. Thus, the telescope stitches together the grandest scales of cosmology with the most intimate question of all, whether we are alone. In doing so, it reframes humanity's place in the universe. We are not just witnesses of cosmic history, but inheritors of processes that began in the first billion years, carrying forward the chemistry and structure of the stars into our own bodies and minds. As Webb's mission lengthens, its datasets are accumulating into a vast library of cosmic archaeology. Each observation, each spectrum, each calibration file is a fossil of an event billions of years past. Astronomers are beginning to cross-match thousands of these fossils, building statistical portraits of the early universe, rather than relying on isolated discoveries. This shift from single deep fields to panoramic surveys transforms our knowledge from anecdote to architecture, letting us see patterns of formation on a truly cosmic scale. Through these surveys, one theme is emerging with increasing clarity. The universe is more diverse than any single model predicted. Some regions of space at high redshift show astonishing richness: walls of galaxies, dense knots of star formation, protoclusters stretching for millions of light-years. Others are almost empty, vast underdensities that hint at the seeds of the cosmic voids we see today. This unevenness tells us the early cosmos was not a uniform soup, but a quilt of hot spots and cool zones, where structure assembled at different tempos and intensities. By studying this patchwork, Webb allows scientists to infer the properties of dark matter. If dark matter is perfectly cold and collisionless, it should form sharp structures at small scales. If it is warm or self-interacting, it will smooth out, damping the formation of small clumps. Webb's map of the earliest galaxies therefore doubles as an experiment on the nature of the invisible. The same photons that tell us of distant stars also whisper of the unseen scaffolding on which those stars hung. This new view does not just enrich cosmology, it humanizes it. We see ourselves reflected in the unevenness of the early universe. Pockets of rapid change, pockets of waiting, a mosaic of emergent complexity. It mirrors how our own histories unfold, with sudden bursts of innovation and long periods of quiet consolidation. The telescope's reach is also changing how we think about time's arrow. In our everyday lives, time feels uniform, ticking forward at a steady pace. In cosmology, however, time is tied to expansion, density, and temperature. In the dense early universe, processes ran faster, distances were shorter, and gravity stronger. This means that an event that might take billions of years today could happen in a fraction of that time then. Webb's data embody this principle, showing galaxies maturing at breathtaking speeds because the cosmic stage itself was compressed. This realization reframes many old assumptions. For instance, the formation of supermassive black holes no longer seems impossible if the clocks of early time ticked differently. Enormous gas clouds could collapse directly without fragmenting, feeding black holes that quickly reached millions or billions of solar masses. Star formation could ignite across entire regions at once, producing heavy elements in record time. Feedback from these events could then ionize the surrounding medium, creating transparent bubbles in the cosmic fog. Astronomers are now building models that explicitly incorporate this accelerated tempo. They simulate the interplay of dark matter collapse, starburst activity, and black hole feedback under conditions of extreme density. The goal is to produce a self-consistent picture in which the impossible becomes natural. This is not just a technical exercise, but a reimagining of cosmic history as a story with its own rhythm and flow. And there is something poetic about this. The universe's earliest moments were like a symphony played at double tempo, frantic, powerful, blazing with energy. We are only now slowing the recording, analyzing each note, discovering harmonies hidden in the rush. Webb is our playback device, letting us hear the fast music of creation long after the echoes faded. The telescope's influence extends even into philosophy. When we look at Webb's images, we are not just seeing distant galaxies. We are seeing a model of emergence itself. Complexity rising from simplicity, order from chaos, structure from energy. These are universal themes that apply as much to minds and cultures as to stars and galaxies. To understand cosmic dawn is to glimpse the rules of creativity at the largest scale. One lesson is the inevitability of surprise. No matter how comprehensive our theories, reality exceeds them. This is not a failure, but the engine of progress. The very act of building Webb, of betting billions of dollars and decades of work on the hope of new knowledge, was an expression of faith in that engine. And reality rewarded that faith with a universe stranger and richer than we dared expect. Another lesson is interconnectedness. The atoms in your body were forged in stars whose ancestors lit up cosmic dawn. The galaxies Webb reveals are not other, they are kin. They seeded the materials that would one day form planets, oceans, cells, and consciousness. In this sense, Webb's discoveries are not about something far away, but about us, here and now, discovering our oldest roots. Finally, Webb invites a rethinking of time, not as a line, but as a weave. Light from ancient galaxies now strikes a mirror we built, becoming signals that shape our thoughts. In that moment, billions of years collapse into a single now. We become part of the same tapestry we are studying. This feedback loop between observer and observed is not a metaphor. It is literally happening as you imagine these galaxies, as the photons become patterns in your neurons. And so, after traveling together through billions of years of cosmic history, we return to the present moment, the point where ancient light meets human imagination. We began at the edge of the known universe, looking back through the golden eye of the James Webb Space Telescope into an epoch when galaxies were still learning how to shine. We saw how the cosmos assembled itself faster, brighter, and more mysteriously than we ever expected. We followed threads of dark matter, the birth of stars, the rise of black holes, and the chemical forges that seeded future worlds. Each block of this journey revealed another layer of the tapestry, until the past became a living landscape rather than a distant memory. In the end, The lesson of Webb's discoveries is not about galaxies alone, but about us, about the humility and curiosity that drive us to build machines capable of catching whispers of light older than our planet. It is about the willingness to let go of certainty and embrace wonder. It is about recognizing that science is not a collection of facts, but a living process, as dynamic as the universe it studies. Now, as you pause at the end of this journey, remember that the photons Webb catches do not only belong to astronomers or to data archives. They belong to everyone who looks up, everyone who listens, everyone who wonders. They are the universe's oldest stories, arriving just in time to be told anew. Thank you for traveling through this cosmic history with Journey Through Time, where the vastness of the cosmos meets the intimacy of a human voice, and where every story of the past is a path into the future. Wherever you are, under whatever sky, may you carry this light with you, a reminder that the universe is still unfolding and that your curiosity is part of that unfolding.